Imagine cracking open a super cold lab fridge. Inside, nothing moves. No gears whirring, no batteries draining. Yet, buried in the dark is a tiny chip that keeps ticking, no matter what. Kinda spooky, right? Here's the thing. We're used to matter changing when we heat it, cool it, squeeze it, or blast it with magnets. Ice melts, metal bends, atoms flip their spins. But this chip does something stranger. Its big change shows up in rhythm. Picture a drummer laying down a steady 4-beat pulse. Now picture a dancer who hears that pulse, shrugs, and locks into her own groove, say, every 8 beats, without ever drifting off time. That mismatch is deliberate, and in physics we call it a time crystal. Until a few months ago, time crystals only survived in perfectly isolated quantum labs. Today's breakthrough? Scientists have wired that stubborn rhythm into a real mechanical part, an ultra-thin membrane you could, in theory, bolt onto a circuit board. Let's break down why that matters. First, what exactly is the weirdness? The researchers drive the membrane with a perfectly regular pulse, tick, tick, tick. Instead of answering in sync, the atoms inside answer every second tick. That's a subharmonic response, a rhythm that's a neat fraction of the drive. And it isn't sloppy. It's an ordered phase, like ice or crystal lattices, but living in time instead of space. Second, they didn't keep it sealed in a quantum snow globe. They coupled the time crystal to the membrane so that each could push on the other. That two-way chat is critical. Real-world devices feel heat, noise, and coffee cup vibrations from the benchtop. By wiring the phase into a movable part, the team asked, "Can the rhythm survive outside the bubble?" Turns out, yes, and we can even tune it. They showed 3 things. 1. You can read the rhythm as tiny shifts in the membrane's position that ordinary electronics can pick up. 2. Gentle nudges let you steer which, every nth beat the system prefers. And 3. Local defects, little manufacturing hiccups, get absorbed into the collective groove instead of wrecking it. That's robustness engineers dream about. Why care? Let me give you 3 quick payoffs. Number 1. Better clocks. A clock is only as good as its oscillator. Here, the oscillator is protected not just by machining, but by the laws of the phase itself. Bump it, and it snaps back on beat. Number 2. Low-power memory. Because the ordered motion lives in a driven, non-equilibrium state, you don't have to pour in huge energy to keep it coherent. That could save precious milliwatts inside quantum processors that already sit in expensive refrigerators. Number 3. Signal cleanup. Feed a messy periodic drive into this setup, and only the frequency pieces that match the crystal's favored submultiple make it through. Everything else averages out. Instant noise filter. And that's just the short list. Think networking. Link several of these membranes and you get nodes that sync only if their hidden tempos agree. Coordinate qubits across a chip, or sensors across continents, without hauling pristine microwave cables everywhere. Big picture, this time crystal plus membrane combo is less a single gadget and more a new type of connector between the quantum world and stuff we can bolt down in a factory. Imagine future hybrid chips where light, motion, and superconducting circuits all share the same invisible backbeat. Labs could literally jam together over thousands of miles, probing gravity, dark matter, or tiny drifts in nature's constants. Let that sink in for a second. Now, you might be wondering, cool, how does this help me? Try this thought experiment. What in your life or work feels stuck in an energy-hungry loop? Meetings, code builds, training sessions? What if you could lock that process into a self-sustaining rhythm that needs only a tiny nudge now and then? That's the metaphorical power of a time crystal. Before we wrap, here's a quick roadmap if you want to play along. Skim an intro article on Floquet time crystals. Just Google those words. Peek at the spec sheet of a real quantum device. IBM and Rigetti post them publicly. Write down one stubborn problem you'd love to test on such hardware. Data security, optimization, whatever sparks you. Give yourself 1 hour this week. That's it. 1 hour to move from, that sounds neat, to, I tried something. So, here's what we covered today. Number 1. Scientists cooled the device to near absolute zero and found a rhythm that refuses to match its driver, a time crystal. Number 2. They wired that rhythm into a mechanical membrane, proving it can survive and be controlled in messy, real-world conditions. Number 3. This stubborn subbeat opens doors to ultra-stable clocks, low-power memory, and noise-filtering links between quantum and classical tech. Number 4. When you stack multiple time crystals, you get networks that sync on their own terms, useful for everything from distant sensors to fault-tolerant quantum logic. Number 5. Finally, the idea invites you to rethink any process in your own life that chews up energy. Maybe it just needs the right rhythm. Take that with you, experiment a little, and keep listening. Because time, crystalline or not, keeps on ticking. Until next time, stay curious and stay on beat.